Okay, in this section, we're studying cylindrical coordinates. They're basically polar coordinates extended to 3 dimensions. So let's motivate it with an example. So what we want to do is start by setting up an expression for the region that is above this cone, this is the top half of a cone, and below this plane. Let me get a rough sketch. Okay, so the blue portion of the cone is the region D. And the first task is to set up a triple integral of some arbitrary function, doesn't matter what the 3-variable function is, but I'm going to integrate this function over that region. So let's imagine it as a type 1 region and set up the triple integral as indicated. So in order to do this, I'm going to need to describe the region in the xy plane over which this region D lives. So it appears to be a circle if I imagine that shadow, and to figure out the sort of dimensions of the circle perfectly, let me take the intersection of the plane z equals 8 and the cone itself. So I take those two equations and I see 8 is 2 root x squared plus y squared. So I'm basically looking at the circle x squared plus y squared equals 16. Okay, so that is the circle in the xy plane. If I'm going to set up the region D as a type 1 region, as indicated here with the differentials, I'm going to let x range between -4 and 4, and then y is going to range between 2 functions. So here's 4, here's -4 for the x values. I draw a line at any x value in between, and I see the top and the bottom. Y is at most this top half of the circle, and at least the bottom half of this circle. So y is going to range, just use the expression here, in between negative root 16 minus x squared and positive root 16 minus x squared. Excellent. And then z gets to range in between this height of the sort of cone and this height of the top plane. So all the z coordinates inside of this cone are bounded below by the cone and above by the flat plane z equals 8. So at most z is 8, and at least z is this quantity here. Okay, so A is to set up this triple integral in that order. Here it goes carefully. And of course, as you can see as I'm writing this here, it's just a giant mess, right, with all these square roots and everything. And the whole point of cylindrical coordinates is, well, polar coordinates do a great job of expressing things like circles. So if we can convert sort of all 3 variables over to a better system, then we'll do that. Okay, there you go. So this is how you would integrate any 3-variable function over the region D if you set it up as sort of a type 1 region. Okay, and just like, for part B, it could be that the function that I want to integrate is the function f equals 1. I might want to do that if I was trying to find the volume of that cone. Of course, there's a better way to do that if you just use the formula of the volume of a cone. Okay, so for example, this would be the volume of the blue part of the cone. All right, well, obviously I don't want to have to deal with these square root expressions. They're a giant mess. So why don't we convert the xy part over to polar? That's a perfectly legitimate way to express the region in the xy plane, that red circle, and z can still vary in between the cone and the plane. So let's convert this to polar coordinates. Well, we know how this works, right? I have to convert the region itself and then convert any expressions that I have involving xy over to r and theta. So the region itself is a circle with radius 4. In polar coordinates, that is expressed as theta ranging from 0 to 2 pi and r ranging from 0 to 4. Okay, and then let me go ahead and put those on the outer 2 integrals, replacing the y and the x. So theta is going to go on the outside, r is going to go on the inside, and then I can convert all the x's and y's over to r's and thetas. Okay, so first off, square root of x squared plus y squared is the square root of r squared, which I can represent as r. And then the dy dx differential unit, I know from polar coordinates, becomes r dr d theta. So this is a much better looking integral to solve than the one up here, and it gives you the same answer as the other one would. So let's sort of summarize what we did when we converted from x, y's, and z's over to r's, thetas, and z's. So that integral that we saw a second ago was represented, okay, and my integrand was 1 in that previous integral, and then I had an extra factor of r. It actually doesn't matter where I put this. dz dr d theta. Okay, so we can evaluate a triple integral using Cartesian coordinates and type 1, type 2, type 3 as in the previous section, or we can compute a triple integral like this, assuming that we've converted the x's and y's over to the polar coordinates. So we're basically exchanging these 3 coordinates for these 3 coordinates. It's just a different way to locate points in 3 space. So it involves, like, if I just grab a point at random over here, if I want to know the cylindrical, these are called the cylindrical coordinates, if I want to know the cylindrical coordinates of that point, what I do is I take a look at its x and y coordinates, convert them over to polar as usual. So this is going to be the r value, and this is going to be the theta value. And then the z coordinate just stays the same. The z is whatever the height of the coordinate is, and those 3 numbers are substitutes for the 3 Cartesian coordinates. So r, theta, and z. Those are called the cylindrical coordinates of the point. And it cleans up integrals sometimes, especially if you're integrating over regions that are round in some way. So the conversion equations we had from polar are just, the exact same. The x and y coordinates are converted to polar this way, and z is just z. So let's take a look at some equations in cylindrical coordinates. Let's take a look at the equation r equals 3. I can think about this in 3 dimensions, or I can come up to the equations and, sort of think about it. So if I am trying to collect together all of the points in 3 space that have a distance like this of 3 rather, what shape am I going to get? So imagine taking a little meter stick and marking 3 out here and gathering together all of the points that have that distance. Well, in the xy plane, you're going to get a circle for sure. And then up here, like this point would be a distance of 3 to the z-axis, making its r value also 3. So it's sort of a circle at any height. Well, that's a cylinder, right? So r equals 3 is all of the points on the surface of this cylinder that has a radius of 3. So let's kind of get this marked a little bit better. Okay, bad picture, but there you go. And you can see it from the algebra of converting the polar coordinates. Saying that r is 3 is the same thing as saying r squared equals 9, which is the same thing as saying x squared plus y squared equals 9. And we know this to be a cylinder in 3 dimensions, right? It's not a sphere, be careful. It's got z as a free variable, and it is basically the circle with radius 3, center 0, 0, dragged up along the z-axis. So that makes a cylinder. Okay, same with these other things. Theta equals pi over 4, I can try and think of all the points that are going to make a theta value of pi over 4 in the xy plane. It's a little bit difficult to do, but you know for sure that anything on this plane would, right? Because if you plot a point on this plane, this is a 45-degree angle here, then when you put the shadow onto the xy plane, then the line that connects it to the origin is exactly this line here. So I'm going to get that, and I'm going to get that. And what's a little bit subtle is that any of the points on the other side of the plane are also going to have a theta value of pi over 4 if you express them correctly in polar coordinates. So imagine a point back here somewhere. You could express it as 1 5 pi over 4. But you could also express that point as -1 pi over 4. So anyway, any single point on this plane here that makes a 45-degree angle to the z-axis, that is going to satisfy this equation right here. I mean, that might be a little bit difficult, but take a look at how I can see it algebraically. If theta is pi over 4, then x is going to be √2 over 2r, and y is going to be √2 over 2r, and in particular, x is going to equal y. Well, guess what? X equals y is exactly the plane that I just drew down here. So we're able to sort of convert polar or cylindrical equations in 3 dimensions over to Cartesian equations algebraically, or you can try and just sort of visualize them manually by thinking about what theta equals pi over 4 means. Okay, let's try this last one, z equals 2. We're not going to have to try too hard on this one because the z-coordinate hasn't changed in cylindrical coordinates. So z equals 2 is still just straight up z equals 2. It's a plane at height 2. Nothing fancy going on here. That is z equals 2. The polar coordinates are not affected at all.